Start recording. Mouse over here, and we are off. Usual boring slides. Logistics. Yep, take a nap. There you go. Nothing's changed there. Nothing's changed. I think Jonas is still out of the country, so I don't think that's changed. I didn't change it from last week. I don't think I fixed. No, I didn't fix this. This is last Thursday's. Last Tuesday's. Lord. All right. Well, never mind. At any rate, mostly what you have now. I'll have to fix this. Mostly what you have now are, I think the capstone design project is due this Thursday, and there's no self-assessment for the lecture today. You won't have a self-assessment for that. Mostly at this point, I'm kind of assuming that your time for this class is largely going into your capstone project at this stage. I've been beating TAs to try and get the weekly reports created and sent back. I had the honor of doing like 35 of them yesterday, so I could get those grades back to you, try and get caught up. Anybody started working on their capstone design project yet? 2 hands went up. Okay, well, at least they're being honest. And then there's a couple of people who are like, oh, my arm's really heavy. I don't quite want to lie, but I don't want to admit the truth. Okay, fine, whatever. The questions keep coming up about the final exam. I literally had somebody say, is there a rubric for the final exam? And I was like, and every time people do that, I'm like, did I screw up and it's not on Canvas, so I have to go? And I'm like on my phone, logging into Canvas, screenshotting it, editing it, and posting it on Discord going, what's missing? So I'm going to go through it again. I've got the screenshots here. They're now in my camera, so I can actually upload them again to Discord the next time someone asks. You have 3 options here. You don't have to take either of the, you don't have to do anything. You can just not show up for an exam. You'll take a 0 on the 20% that the exam represents, but you won't fail the class because there is no mandatory pass the final to pass the class. You can take the in-class 75-minute final exam on December 7th. And that's going to be based on true and false questions. I was originally just going to use the self-assessment questions because there's several hundred of them. And it's like, who's going to spend the time to memorize them? But then somebody on Discord was like, oh, no, you really shouldn't do that. So I'm like, okay, fine. So I'll tweak those. I'll make all the true statements false and all the false statements true, and I'll reword all of the multiple choices. I don't know, something like that. That's optional. You don't need to take that. You don't need to show up on the 7th of December for the regularly scheduled class session. Doesn't matter to me. You don't have to take the one on the 22nd of December at 7 p.m. Again, it doesn't matter to me. If you take one or the other or both of them, the grade that you get on the final will be the max of the 2. The in-person written final exam will have a 2.5-hour limit. And it will present you with a selection of design scenarios. You will pick one of those design scenarios, and then you will design a solution to whichever one you picked. And there is a very long rubric, and that will be included in the pieces of paper that I give you for the design. How much of your final grade do you know before December the 7th? Well, so you should know everything in the self-assessment category and the design projects. That should all be done by December 7th. Done now. I'm probably behind on something, but on the 7th. Yes, well, I'll make a comment on that. So let me finish this first. So in the in-class final exam, 40 questions. My goal is to draw from the self-assessment but I'll be making some modifications to that. I have questions that I used last term as well, and I might pull some out of that. I'm fighting with the questions. I've managed to get them to export from Canvas, and it's like all in XML, which is just absolutely painful to turn into something reasonable like JSON, what I use for generating the tests. The in-person final exam will be this design project, one design scenario that you get to design. And here is, in fact, I know you don't have to read it. It's actually on Canvas. It lays out what I'm looking for, which is I want to see how well you can apply the design skills that we've been talking about in this class for distributed systems problems. Do I expect that you're going to come up with a good design? Probably not. What I'm mostly going to be looking at is, do I remember what Paxos is? Do I recall anything about data replication? I kind of might remember a couple of cases of failure. And I don't want you to fail on the design, obviously. But that's the goal. I mean, the goal for both of these is to basically test the same thing, which is how well can you apply the principles we've been talking about in the class? So the capstone project is due on the 7th of December. I cannot make the due date for that any later. However, someone suggested, and I had been thinking about it anyway, I can allow you to turn it in late. So the official due date is December 7th at 11:59 p.m. is the last possible moment that I am allowed to assign a due date, but I won't grade them before December 22nd at 11 p.m. So that's the best I can do. And the reason I thought that was a reasonable compromise is because I suspect most people won't want to take both finals. But even if you do, then you probably try to shoot for getting your capstone done sometime between two of them. That way, if you want to take the optional final on the 7th, you can study for that and then use the time after that to defer doing anything on your capstone project until December 22nd at 7 p.m. when you say, all right, it's time to stop gaming and actually write, finish my capstone project. And if you look at Canvas, it will actually say that you can, supposed to say that you can submit it until the 22nd at 11 p.m. I promise you I won't start grading it at 11:01. Yes? Only that I have to grade it over Christmas. That's the penalty. So my penalty is because UBC decided to give us the worst possible date for the final, I'm trying to be as reasonable as I can here. But I'm not going to penalize you. What's the point of giving you a late date if I penalize you for it? I mean, I thought about that and I'm like, no. That makes it just too complicated. It's already complicated enough. I don't need to make it even more complicated. So, Cortana? I'm pretty sure I didn't say, hey, Cortana. Now I did. Great. I'm waiting for Master Chief to start talking. So I kind of went a little bit different direction for the failure of the day. I said, let's look at some work that was done to look at not just a single failure, but instead classes of failures. So we've talked about individual failures, and yet you probably noticed there are some common patterns to these things. Could we actually build tools that would allow us to identify those common patterns in a more systematic way so that we aren't shipping schlock out the door? We're actually fixing and finding these problems before it gets too late. And a particular class of problem, which came up last week in conversation, I think, sidebar conversation, was what do you do about upgrades? Anybody ever had to do a database upgrade? Change your schema, update the software? I mean, usually, if it's updating your software for your own personal database, you're like, well, I'm just going to install and pray it works. When's the last time you installed an app on your phone that updated its database and trashed it? happens. But a lot of times it doesn't. And we've kind of grown to expect that we can do in-place updates of pretty much anything, and it'll just work. We don't need to back it up. Upgrades are one of the most dangerous things we do in distributed systems, in live, real, running distributed systems, because they have to be done either. Okay, there's two ways we can do it. One, we can take the database down, we can do the upgrade, we can bring the database back up. Sometimes the database doesn't work right when we do that. One of our failures was actually when the backup process for the database broke because we'd upgraded the database, but the script that did the backups relied on a specific version. So when it didn't see the right version number, it stopped doing the backups, which of course, when do you discover that your backups don't work? When you need them. You're like, it worked when I tested it initially, but I haven't looked at it in the last 6 years, and somewhere along the way it broke. And that's not the right time to discover that your backups are broken. So, an interesting point that's happened increasingly over time is that we don't have downtime windows. And when it was just a company or maybe a single office even, upgrading the database is the kind of thing that people came in on the weekends and did. It is certainly one of the things they can do during that maintenance. They're probably updating something. They could be replacing hardware. They could be updating their database. They could be updating the framework that they're using to render their website. All sorts of things like that. I can tell you, Amazon does not take their website down. Not willingly. It's been a while since the Amazon website crashed. And I assure you that Amazon has continuous update working. This isn't a new idea. One of the fascinating things, we were talking about operating systems earlier on, one of the fascinating things I saw years and years ago was that in the very early cluster systems that Digital Equipment Corporation built, they could actually upgrade individual CPUs in a cluster. They would literally do rolling upgrades where they would take a member of the cluster out, they would upgrade it, and then put it back in the cluster and then go to the next machine. And they built their software to do that so that there was no downtime. These are literally machines that were, in the end, designed to run for years without rebooting. That's a really hard problem. But that is increasingly our expectation. We're going to be able to keep using our services. Our database isn't going to go down. We're not going to have, sorry, this website's down for maintenance for 3 weeks. How do we get there? How do we do that? So this software upgrade is a real problem. And there's this cool paper from SOSP 2021. It was during the middle of the pandemic, so this was virtually online in Germany. Actual SOSP 2023 was physically in Germany because it was supposed to have been in the same location. Next year, it's in Athens. No, that's Eurosys. Where SOSP? I don't know, but Eurosys is in Athens. I'm going to Athens. It'll be April. It'll be nice weather. Cool paper. What they actually did was they looked at the class of failures that they saw in production systems. This wasn't stuff they were making up. This is why I thought it was a reasonable fit for the failures of the day, because these are production systems. This isn't academic stuff. The academic work is based on production systems. And what they found was they could identify patterns in terms of severity, root causes, how to figure out what happened, what condition was exposed that caused it, and then strategies to fix it. They built a tool that allowed them to test specifically for these upgrade failures. They then ran it against existing databases, and they found 20 previously unknown upgrade failure cases in 4 different distributed systems. That's a lot. They didn't fix one problem. This wasn't a DevOps problem. This was a Cassandra problem. Anybody know what Cassandra is? Yeah, it's a Paxos replicated database. Or maybe it's Raft replicated. I don't even remember which one. But it's a consensus replicated database. And people use it at scale for large amounts of information. So, of course, it's important that we be able to try and make it as error-free as we possibly can. So this is a cool example of going beyond just focusing on an individual failure and instead looking at classes of failures and building a tool that allows you to eliminate them. And this, if it were a capstone project, I'd give it about a 90%. So, bar is not too high. You'll be able to. I'm kidding. You guys are like taking it half seriously, or you're just. So that's interesting, and I encourage you, if you're interested in this area, go look at the paper. The link is actually in the slides. The paper is very interesting. Nice piece of question. Yes. They actually do read those papers. About 50% of the papers that go on at these conferences are by people in industry. And they show up. Part of the reason they show up is because half of the papers are from industry. And the other reason they show up is because they're constantly trying to recruit people in distributed systems. Getting people with this skill set is really hard. I don't know why. Pretty easy stuff, right? How hard could this possibly be? Just got to get a couple of computers to agree on something. Today I'm going to be talking about distributed data analytics. And again, what I said was the last couple of lectures here are just going to be more sort of generally interesting topics. We have talked about MapReduce. So I'm going to dive into it a little bit more. And then we're going to talk about a different distributed processing system called Spark. Is an Apache project. The MapReduce, well, that's not quite because Hadoop is more GFS than it is MapReduce. GFS was built to support MapReduce. Then they came back and built what is the other system called? I don't even remember right now. Google replaced their data. One of the things that we notice when we start doing data analysis is that frequently what we are doing are problems that are trivially parallelizable. In other words, it's a big problem, but we can break it up really easily and parallelize it without a lot of effort. So for example, the original use of MapReduce was at Google, and what they were doing is counting the number of web pages that point to this page. So they're looking for the fan-in of the internet. Think about the internet as being a big graph, which is a perfectly reasonable model. You want to know how many other sources point to this page. Because if lots of other people point to this page, then this page is probably more valuable than that random page that you put up 3 years ago that's got one link from your website. That's at least the theory behind it. Of course, the problem with any of these metrics are that as soon as somebody knows the metric you're using, they will then manipulate the data because they want to get ranked higher. And that's been a persistent problem with search engine optimization, or SEO. Any of you ever heard of SEO? It's like a big business. And the big providers they used to try and minimize the ability of people to hack the SEO, and these days they just simply sell all the advertising space they can, which is how they've conquered the SEO business. Just pay for presentation. The point here, though, is this is a very easy process for us to just simply break up, scatter around, count up, and then pull all the data together and collate it at the end. This is what we call MapReduce, which is we take these large data sets, we split it up into a bunch of small pieces, which we farm out to different nodes. Those nodes then do the computation, and they send back a data set, which we can combine with the data set from other nodes and reduce it down. So you saw that there were 2 links to that page. You saw there were 5 links to that page. I didn't see any. We add them up. There's 7. Now, of course, we're not going to do this a page at a time. We're going to do this in very large numbers. But it allows us to break the problem down and make it scalable. This is a very straightforward use of distributed systems. You see any challenges in this? Go ahead. You certainly limited this. The first thing I said was trivially parallelizable problems. It turns out that MapReduce doesn't work well for actual neural nets, for example. When you start trying to build neural nets and just build a distributed system that computes large neural nets that can't fit on a single computer, MapReduce doesn't solve the problem at all. Why? What makes PageRank? What makes the PageRank algorithm, which is counting the number of links into each page, what makes it trivially parallelizable? Commutativity of addition. So the fact is that, and I don't have to communicate those results back and forth frequently. Basically, I need to get the data moved down, but all I do is send back just results, and those results can then be merged at the end. In a neural network, does anybody know how a neural network works? It's like 1 step forward, 2 steps back, because you send information from one layer of the neural network to the next layer of the neural network, and then the next layer of the neural network does its computation, recomputes its weights, and then sends things back to the previous layer. So you're literally propagating information forwards and backwards and forwards and backwards. There's a lot of communications. And because the layer before you is dependent upon your back propagation, you can't do your next round of computations until you get the previous round's results. Now, people have figured out that you can be a little fuzzy about some of this, and sometimes you only sync up every so often. So there are ways of making it faster and better, but it doesn't fit the MapReduce model very well. So MapReduce really does rely on being able to divide the data up across the nodes to balance the load across these things. For highly decomposable problems where you have commutativity, kind of like what we saw with eventual consistency, right? Make things commutative, and eventual consistency was pretty easy to accomplish. If you don't have commutativity, eventual consistency doesn't exist. Can't solve a large class of problems, but many of the problems we can solve are worth doing this. So we remember these techniques, we learn these techniques because they are applicable for optimizing the performance of a particular kind of problem, solutions for a particular kind of problem. Question? Yes, that's exactly the point I was hoping somebody would bring up. My gosh, we're moving a lot of data. So when Google did MapReduce, the very first thing they did was they built the Google file system, which was this huge global file system, which wasn't really a file system, but I'm a file systems person, so I look at it and kind of get grossed out by it. Huge collection of data, and in theory, anybody could access anything anywhere. It turns out the hardest part of building these sorts of data analytics systems ends up being data movement. Either we make lots of copies of the data, or we centralize the data, but now we have to worry about the cost of going and fetching the data. And we've got to update it. And remember, the larger our network of storage servers are, the more likely we are to experience failures. And what have we just spent the last, I don't know, N weeks studying? How do we get rid of those, or how do we deal with those kinds of failures in storage? What do we do to make sure we don't have single points of failure? This would be a good question on the final because this is like fundamental to the whole class. You've already volunteered. I want somebody in the back. Come on. You're being quiet. I will walk back there if I have to. Here, I can do that. I can walk to the back. How do we eliminate single points of failure in a storage system like a database? Replicate it. Wow. Are people just afraid of saying the wrong thing even though you know that it's the right thing to say? That interesting social pressure of like, oh my gosh, I could be wrong. I'm always wrong, almost always. So what do? We distribute all this data out so that we can get access to it, but then we have to worry about the fact that we could have individual pieces of it fail, so we start replicating them, and now we've created this hideously complicated mess to implement. What is our scarce resource here? It's not storage. Storage is cheap. You can slap a couple more petabytes of storage on these days, and it fits in less than a rack now. Used to be you had to buy a whole rack to put 2.5 petabytes in there now. And I think you can probably put 2.5 petabytes in like, 3U. Yeah, it's the network that's going to become our bottleneck, isn't it? Because when we talk about point-to-point link speeds, how many of you actually have an Ethernet, an actual physical Ethernet connection someplace in your premises where you live? Right. Maybe it's the one that sits in the closet and everything else after that is Wi-Fi. What's the fastest you can get from Wi-Fi? Not very fast. Maybe a couple of gigabits these days. I don't know what the latest 802.11 blah, blah, blah is. Mostly you're probably going to get under 100 megabits. But 100 megabits is good enough to game, so what more do you need? I don't know. How many of you actually game? How many of you game over Wi-Fi? It sucks. It works great until you live in an apartment with 485 other people who are all using Wi-Fi at the same time, and you find out that it's shared bandwidth. It's like having cable internet. What do you want to do? You want to have a wired connection because that runs faster. What's the fastest wired connection you can get right now? Money's no object. I've even mentioned it in class. This would be a great question on the final too. Currently, the fastest network cards you can buy are 800 gigabit. Whip out your American Express card because it's going to cost you a lot to buy an 800 gigabit transceiver. What's the problem with having a really high bandwidth point-to-point connection? I talked about it last week. Data center. What's at the top of the rack in the data center? I literally use the term top of rack. When you start talking to data center people, they talk about the Tor switch. The top of rack switch. The problem with the network is it's a shared capacity. You're not using an 800 gigabit connection at home because you don't need it. Even your whatever it is, 3 gigabit connection that you can get from your ISP, which I think is about as fast as they possibly offer these days, is probably more capacity than you're ever going to use. But you're promised, let's say you're just using the gigabit service because that's pretty common these days. So you're promised the 1 gigabit service, and you're promised the 1 gigabit service, and you're promised the 1 gigabit service, and I'm promised the 1 gigabit service. Guess what? If we all start sucking down 1 gigabit at the same time, it's not going to work because the backbone can't have more than 800 gigabits. So do a little math, that means that there's 800 of us who have all been promised 1 gigabit. Somewhere there's going to be a fat pipe that's going to be running at 100% capacity. And I guarantee you those pipes don't actually run at 100% capacity. So the point is, we have a scaling issue. When we start distributing all of this data around and we add this replication layer to fight against these problems, now we have a network bottleneck. And nothing we do is going to be able to completely overcome that bottleneck. So we're going to have to find ways of efficiently and effectively using that bandwidth. The most effective way of using that bandwidth is to make sure the data is close to where it's needed. If I have 100 racks, I don't want to be going all the way up to the aggregator switches and back down to some other rack. I want to be going up to my top of rack switch, down to my storage, back up to my top of rack switch, and then back to my compute engine. That's going to be the most efficient path. Or maybe I actually have storage in the compute node, but that's not the way we build these things. So that's something we have to keep in mind. Moving the data is really hard. It's very expensive, and it's the thing that will slow us down. We can build these systems out, but then we have to replicate them because stuff fails. So we replicate the data out. Maybe we're very careful about where we replicate the data out. So now what we have to do is start thinking about, as we break this problem down, I want to make sure that I put the parts of the problem that are parallelized close to where their data is located. Now you have a placement problem. And a lot of the work that is done in these systems is figuring out how to get the data and the compute close to each other. It is completely fair to say that the way that you store your data should be dependent on where you are performing your task. Right. So the question is, okay, but what happens if I have a bunch of different tasks and they have very wildly different behavior characteristics? How am I going to balance this out? And the answer is, you're probably not going to design the system to do it that way. You're probably going to segregate those so that you can make them more efficient. However, suppose that I have a compute-intensive task and I have a storage-intensive task. I might co-locate those because the storage-intensive task is mostly spending its time waiting for the data to get back from the storage, and the compute-intensive task needs lots of CPU power, but doesn't have a huge amount of data that it's moving around. And so you can do some balancing of things like that to make more efficient use of the resources you have. So sometimes you want to mix your loads in order to use your hardware more effectively. But I can tell you, this is a really, really hard problem. This is the kind of problem that people spend lots and lots of cycles on. A big thing still in doing these kinds of placement activities is to use AI. Try to predict things. We try to measure and analyze things. We try to determine if we need to move the data around or if we need to move the tasks around. But the more that we do that, the more that we expose the infrastructure and the details of the infrastructure to the applications themselves, the harder it is for us to build general purpose applications. Application programmers just simply want to say, I've got this generic compute device with some generic storage, and I just build it, and I don't have to worry about where things go or how they behave. And this is a constant tension in systems. There are a whole class of papers where people say, if the application can tell me what its caching behavior is, I can build a more effective cache than discarding the least recently used stuff. And those are great papers. The problem is, and this is me speaking from decades of experience with this, when you talk to an application programmer and say, what is your access pattern to your data? It's the same look that, do any of you have a dog? Do you ever try and explain a complex computer science concept to them like, hey, this is a mouse and you click on the button here? Something really complicated like that, right? And they just give you that look, huh? That's exactly the look you're going to get from the application programmers. They don't have any idea what the access patterns are to their data. So this is really cool stuff from an abstract technology perspective, but in the real world, no, what happens is people slap their crappy applications on there, they find out the performance sucks, and then they say, how do I make your system work better? So the systems people actually sit down and say, well, we're going to look and see at what your access pattern is, and we're going to try and optimize for that. We try to infer their behavior by watching how they're using the actual system. This is one of the fun things about systems, but it's also annoying because you optimize it for a particular workload and then somebody else comes along and they have a completely different workload and then you find out it all goes to shit because your assumptions are now wrong. Networking, load balancing, how the application uses the resources, all of these things become factors. So we have different techniques that we use to optimize this performance. A common one is pipelining. Pipelining is very common, and if you think about it, why do we pipeline? Well, that's because it keeps the compute and the data that it needs for performing that compute close to each other. And then the next phase uses output from the previous phase with a different set of compute. And now we do that as well. And so if we build this correctly, we get some of that locality and more effective use of the resources. I know people who've been able to get whole PhDs out of just looking at ways of optimizing these kinds of data pipelines. It's very common now in data centers for them to use virtual network functions. They literally abstract out the things that we do on the network, manipulate the data. Like you can have a VPN network function, you can have a load balancing network function, just a variation on a proxy. You can have quality of service network functions. And they literally take these little blobs of software and plug them together. And then somebody else comes along and says, I can come up with a more efficient way of plugging these pieces together and getting them to get an end-to-end data flow that is better than what we've done before. Oh, here's your PhD. Go work for Cisco. Palo Alto Networks, Juniper Networks, Cisco, let's see, one out in Burnham. They make switches, actually make wide area stuff, but can't even remember the name, and it's one of the companies that Sheraton started, so at any rate, it doesn't matter. All sorts of companies that do this stuff. There's big, big money in this. And they hire people who can solve these kinds of problems. Ah, question in the back, I love it, yay! They're actually way back there. Using the neural network, okay, so we're building a neural network on a distributed system so that we can scale it up to having, some billions of neurons and multiple layers and whatnot, yes. Right. Well, this is one of the tools that you might use in order to mitigate some of that, yes, would be to look at it as a series of pipelines. And that's, in fact, the way that I've seen they typically make this faster is you don't backpropagate every round, you backpropagate periodically. You kind of batch things up and then you backpropagate. And then what people do is they show that there are bounds on how far away from optimal you are. So you're willing to take slightly fuzzier results for getting the answer in 1/10 of the time, right? Well, you can. It's the perfect versus the good argument. Never let the perfect be the enemy of the good. So getting an answer in a time frame that I can use it in is better than waiting until I have the perfect answer. You could take that task that says this node is going to do this, and then this node is going to do that, and it just happens to be that the output of this node is the input of the next node. That's really all that pipelining ends up being. So it is a technique for taking a larger task and breaking it down. You can parallelize this because you can then have multiple parallel pipelines. And the way that you would tend to organize those is, again, around locality and trying to optimize the resource utilization of the. So you're dividing the work into smaller numbers of tasks. You put a small number of those tasks on an individual node. Usually this is faster because we're specializing the system a little bit now, aren't we? Not a lot, but a little bit, enough to get some performance benefit out of it. We tend to do this in chunks. So one of the interesting benefits here is that if I have several different tasks on a single node, I can stagger them so that they finish at different times, so they're sending their data to the next part of the pipeline at a different time than the other parts of the pipeline. So what are we doing? We're spreading our use of the network out, because it's not just bandwidth that becomes our limitation there, but also the burstiness of our traffic. I mean, if I only send one packet a day, but that packet is a terabyte in size, that's not a great model. But if I can split it up and I can send, a gigabyte every, I don't know, 5 seconds or something, I spread it out. And so again, these are the kinds of techniques you need to start thinking about when you build these things. Sometimes you actually have problems where you can parallelize the model. So this is different than the pipelining model where it was serial. This time what we're doing is we're taking the problem, we're breaking it up into parallelizable chunks. The problem with this is more what happens in neural networks. Actually, when you start building these neural networks, try to build model parallelism. So you pass the inputs to all the nodes, and then you combine the output of all the nodes at the end, but now you have to worry about the dependencies. It's the dependencies that kill you with the neural network example. Graph processing, same thing, right? Where you do an operation here and it has effect on other attached or related nodes. And so you have to propagate the changes there, but then that changes the way they behave, and then that propagates back. You have these kind of waves that are going back and forth between neural networks. I think are in some ways easier to think about because their model parallelism is that they're layers. Graphs are harder because they're not layered. Graphs are more general than what we typically see with neural networks. Neural networks are a restricted kind of graph. So when we use model parallelism, we're dividing the data across the nodes. We do less processing in the individual nodes, but we're passing input to all of these nodes, and then we process it. We do a little bit of processing, and then we combine it at the end. So now what we're doing is we're moving the same sets of data in, and each of these is performing some operation on that common set of data. Maybe we're doing a set of different computations that are on the same data but are different computations. I'm computing checksums, and I have each one of those that's computing a different checksum. Again, you still have to handle dependencies. Once the input of one of these depends on the output of another, you're going to have to make sure that you get a correct ordering there, otherwise you're going to get garbage. MapReduce is one of the oldest and simplest of the techniques that we use in the systems environment. Now, the problem I have with MapReduce is that when I first saw this paper, I said, but the database people had been doing this for 25 years. That's true. They had been doing this for 25 years, but this paper was a systems paper. The systems people looked at it and they said, wow, this is really cool. And the database people went, we've been doing this kind of parallelism stuff for 25 years, so why do you people think it's great? But it is the same basic idea. And that was Jeff Dean and company at OSDI 2004. So were any of you born in 2004? 2004? I'm trying to think. I'd be like early 20s, so yeah, maybe just barely. But like you were a little, little kid. don't worry, one of these days you'll wake up and look in the mirror and you'll go, wow, I'm just as old as that old fat dude that taught the 416 was. Man, what happened to me? Hadoop is an Apache project that was based upon the work that Google did for the Google file system and MapReduce. And Hadoop is still out there, it's still in use, it's still an Apache project. The AWS infrastructure has a number of different components that actually provide this functionality. I think they actually provide something that's comparable to Hadoop. Pretty sure they do. So in MapReduce, the input is a set of key value pairs where we have a mapping function that takes a unique key value pair and spits out a new key value pair. Wow, isn't that cool? It's just a transformation. It maps one key value pair to another key value pair. And then a reduce function takes an input, takes as its input the output from the mapping layer, and its output is a final result. So in other words, we all tally up our link counts, and then we add them together, and we're done. On top of this is an orchestrator of some sort. Because orchestrating this is a very important part of the process. That's why I was rambling on about resourcing and loading and storage and moving data around, because that's the job of the orchestrator, which is often the most complex part of this system. How do I make this data flow efficient? How do I gather those results quickly and effectively? Can you see any problems that might arise as you increase the number of nodes that are processing this data? What is the first thing I talked about in this class? What is it I talk about at the beginning of every lecture? Failure. Could anything possibly go wrong here? If I take 1 million minions and I give each of them a little task to do, is there any possibility that one of them might not finish the task? Yeah. In fact, it seems pretty likely. Are they all going to finish their tasks at the same time? So one of the downsides to using a MapReduce model is that you can't have the final result until the slowest minion is done. One of the jobs of the orchestrator is to deal with this, is to handle this problem of what we call tail latency. How can I distinguish that a minion's dead versus just lazy? How do you know if that message is lost or delayed? Same problem. Same problem we started wrestling with weeks and weeks ago. You don't. So the orchestrator basically says, if I haven't heard from you in some period of time, I'm going to declare you dead. And the way I'm going to fix that is I'm going to take your task and give it to some other node to do. The tighter the bound is, the better my tail latency is, but the higher the likelihood that I am doing duplicative work is, because I might give up on that minion, farm it off to this other minion, and that minion gives me the result. Question in the back. Wow, this is a record. 2 in one session. Cool. Right, so there's another problem. Wow, but wait a minute. Maybe it's actually the buggy code that the application gave us to do the map function or to do the reduce function, and it's killing the node. Maybe that node doesn't have as many resources, or some of my nodes don't have as much memory as other of my nodes. Because I didn't even say that all the nodes have to have the same resources. And we know applications programmers. What does an application programmer do when they call memory? They try to allocate some memory and it fails. They die. The application dies. So running that task on another node may not fix that problem. There could be bugs in the code. That's a different class of failure completely than the cleaning lady unplugged the rack because she had to, or they had to. I should be careful. The cleaning person, because they had to vacuum the carpet and that was the only outlet available. Fine. Lots of things can go wrong here. Things can get slow. We can have network failures. We can have node failures. We often can't tell which is which. And the orchestrator is responsible for managing these things. So the orchestrator, I'm using the term orchestrator even though the slide says master because master is no longer a politically correct term. Ask Git. So it orchestrates the workers. It deals with the I/O, moving the data around. It deals with failures and deciding where to put the map and reduce function. Pretty fun. The word count example, you have a collection of files. You want to know how many times a given word occurs. Well, this is trivially parallelizable. I'll just give each of you a bucket of words from Wikipedia. Take the first 100 million pages, you take the next 100 million pages, you take the next 100 million pages. We just keep adding up the words on it. And then we collate it all back at the end, and now we know how many times different words occur. So our input is a file, key is the file name, the content is the value. The output is a file with the key is a word, and the value is how many different counts we have. Our reduce function then takes the file with the word and the list and it totals it all up. That's our reduce function. This was what we ended up using in the original Google work. The reason that Google exists at all, because of this PageRank mechanism, was exactly this problem. They just go look and see how many references there are to a given page. It's a cool class of problems. Lots of problems don't fit in a MapReduce world. But we can optimize things by combining many of the techniques that I've been talking about, where we have data parallelism, pipelining, model parallelism. And it turns out, surprisingly, we can get an awful lot of work done in the MapReduce model. It's still good enough for Google. Lots of decisions that you have to make when you start building a MapReduce system. How do you track your master data structures? How do you deal with locality? I mentioned the locality problem, so this is something you'd have to think about in your design. This would be a great question for final, right? Design a MapReduce system, and what are the issues that you have to think about? Well, you have to think about locality of the data. You'd have to think about the CPU resources. Where are you going to put the intermediate data? Because remember, we had an output. So where do we put the output? Because the output needs to be close to where we're going to do the reduce function. It doesn't need to be where we got the input, the map function. So maybe we're going to be putting that data in a different place than we got the input data from. There's no reason those have to be in the same spot. What is the granularity of our tasks? The finer the granularity of our tasks are, the more flexibility we have for placing them and for managing our resources. But we get a lot more management overhead then. So coarse granularity could be a big win because we don't have as much management overhead, but now we may not be able to use our resources effectively. I already talked about fault tolerance. Of course we're going to do replication. How do we detect failures? How do we detect stragglers? How do we re-execute after a failure? Mentioned those issues as well. So those are things you'd have to think about in a design. What are the semantics of failure? What is our consistency model? What are our safety guarantees? How are we going to back things up? How do we protect ourselves against things going wrong? And so the input, we replicated that. But the intermediate files, are we replicating the intermediate files? Maybe we do, maybe we don't, because maybe we can recompute those intermediate files, in which case then it's not worth backing them up. So these are design considerations you have to think about. Lots of limitations in MapReduce. There are problems with re-execution because once your failure rate starts to get to a certain point, you don't make any forward progress. You end up restarting things, and the failure rate's too high, and it takes too long to recover from it. So you end up building fault-tolerant mechanisms where you use this intermediate data availability, and now you have a cost associated with putting this into a serialized format. Map function was written in Java, and the reduce function was written in C. You have to have a common data format. You have to agree on what that data format is, and that has an overhead to it as well. Data movement, data amplification is an interesting problem. Maybe the intermediate data, and I've seen workloads that are like this, where the input data is actually fairly small, and the intermediate data then blows up. UBC does a lot of work in genomics. It's one of the top research institutions in genomes. And one of the people in my lab at the time worked with, he got a Nature paper out of that work, actually. And a CS guy with a Nature paper is pretty rare. There's like third author on it. There's like 400 authors on the Nature paper, right? So third author was a pretty big deal. The other two were botanists. Turns out that UBC is the place to go if you want to research the genome of the sunflower. We grow a lot of sunflowers here, and apparently it's really important. And it turns out the sunflower genome is about the same size as the human genome as well. It was like, wow. And so they have these whole pipelines of work where they take input and then they process it, and then they process it again, and they process it again. And they literally get 100x data amplification for some of the intermediate stages. So they don't want to store it all. But so you kind of get this model where you have to store it for a while, and then you throw it away because you can recompute it. Sometimes it's compressible, so you compress it down. You have to think about these things. Yes, the last one is a really important point. Often people have cost constraints for my data is so large, I'm not using SSDs, I'm using the cheapest hard drives we could get. It changes my failure model. It changes my performance characteristics because those drives are going to be slower. So how do I deal with these things in my design? An alternative to MapReduce is Spark. RDDs are resilient distributed data sets. So this was a model that is focused around how we distribute the data in these very specific packages called RDDs, because it turns out that managing the data and managing its placement and managing its movement is really important when we build these kinds of data analytics systems. This was so much better than MapReduce, aka Hadoop, because that's the open source version of MapReduce, that people used it for all sorts of fun things. It is used for graph processing workloads, streaming data workloads, SQL data workloads, machine learning. Now we're back to neural networks again, right? It supports, RDDs were generic. They weren't really tied to a particular language, so it is still commonly used and supported by Java, Python, Scala. Java and Scala being both JVM based. But the point is, these are common container models for moving data around that work across the languages and do it in an effective way. Essentially, they came up with a clever way of encapsulating the right set of data that you needed to perform these operations. So it optimized that. But in order to get cross-language compatibility, you need to serialize the data. You need to put it into a format that everybody else can understand. It's the same thing we do on the network. Put packets out on the network. We have to agree on what they're going to mean when they get to the other end. This is commonly used. Spark is commonly used on AWS with Kubernetes, for example. Kubernetes is an orchestrator platform. So we're going to do data orchestration with Kubernetes. Kubernetes is used for all sorts of things. Docker containers. The containerization fits really well with RDD because our tasks can be containers. The whole microservices model ends up being a very natural fit for data analytics precisely because the pipelining that I was talking about before ends up being a really good fit for clearly encapsulated data elements, RDDs. Apache Spark is an Apache open source project that implements Spark, which is based on the paper that's referenced there. You had a question. Right, Docker containers. I thought they used it for actually distributing the data as well, but I'm not sure. I'm not. This is like, I know how Kubernetes is implemented, but I'm not actually quite sure what they use it for. Sort of like I know how to build databases, but I'm not that sure when you start giving me complex SQL statements. Anybody here know SQL? I'm sorry. Things that humans shouldn't have to be forced to learn. You think SQL's bad? Wait until you look at GraphQL. Ugh, that's bad. So part of the way that Spark ends up getting better performance is by doing a better job of keeping the hot data in memory. Because the fastest SSD is still orders of magnitude slower than memory. But memory is more expensive. So we have to use that memory effectively. And so what happens in Spark is often that the intermediate forms stay in memory. They don't actually get written out to storage. That doesn't work super well if you get a large amount of data amplification. So you have to think about, what is the data amplification in my problem going to look like? How can I combat that? I already mentioned one of the common techniques is compression, because it turns out that often that explosion isn't because there's more data, it's just because there's more bits. But the actual amount of information in those bits is still relatively small. And so you can use various kinds of compression. One of the benefits of keeping it in DRAM as well is you don't have to serialize it, because you're not going to stick it on disk, because nobody else is going to need to understand it other than just you. So that makes it faster as well. So RDDs, yes, right. RDDs are immutable. I have mentioned this idea more than once. When you make something immutable, it's so much easier to reason about because it can never be modified. It simplifies a lot of our tasks. Think about what we did when we built Paxos. We didn't build Paxos because we were trying to keep track of immutable data. No, we kept Paxos around because we needed to mutate our data, and that got a lot more complicated. Immutable data, not so bad. So what we do is we create new RDDs by transforming old RDDs. Kind of like in MapReduce, where we had mapping and reducing functions. Here we have more general purpose functions. You know, these map join and filters. We can have more general purpose operations on them. And interestingly enough, the RDD actually shows you its provenance. It shows you where it came from. How did I get to this RDD? Oh, it came from this previous RDD, and we applied this particular operation to it. So you have a way of reconstructing things, of getting back to where it came from. So that helps with the backup problem because it provides us with a recovery mechanism that doesn't involve any storage at all. If I don't have to store anything at all, it's way faster. I mean, I'm a file systems person, and I can tell you that one of the important lessons a long time ago was, if you can defer doing any work until it's no longer needed at all, you save the most time. And the reason that's important is because Werner Vogels, who's at Amazon, has been for a long time, in 2000 wrote a paper in which they did a performance study on standard file system operations on Windows NT 4. And they found that 55% of all files were deleted within 30 seconds of creation. My observation is that means the magic number there is to make sure you don't write anything out for the first 30 seconds it's around. Keep it in memory, because odds are you'll never have to write it at all. And no I/O is always faster than any I/O. Even the fastest I/O, even putting it out into DRAM, let alone putting it onto an SSD or a disk. Pretty cool when you think about how can I optimize these things away by just simply not doing unnecessary work. Why is that okay? Because I still would have to deal with failure. Yes, this only makes sense when the cost of reperforming the operation is significantly lower than the cost of storing this data relative to the likelihood of failure. If failure is rare, the occasional recompute is a good choice. If failure is frequent, the occasional recompute, well, it's not an occasional recompute. Now it becomes a frequent recompute, and now it's not a good choice. So again, you see that there are lots of interesting problems you have to think about as you design a system that is going to try and use something like Spark with these RDDs. Here's an example. I don't want to spend a lot of time on it. Slides. It's just how do I build these things? And this is actually built on top of Hadoop, HDFS, the file system. So Spark came along 12 years ago. Spark came along a while ago, and at that time, Hadoop was the primary platform that people were using. So it's saying, well, here, how we're going to build our RDDs and propagate them through storage system. And we're going to coexist with stuff you've already got. Again, we have transformations on the RDDs where we can perform a variety of different operations. We have some actions we can take on those. Never modify the RDDs. We only create new RDDs that are derived from the old RDDs. There can be dependencies between the RDDs. Well, there are dependencies between the RDDs. We can depend upon these things, but it's not up to us in Spark to define those dependencies. It's actually the responsibility of the application. We don't know what the application dependencies are. So this is one of the hard parts about using Spark, is that people have to build their workloads so they understand their own dependency model. I rely on this data in order to do this computation. You cannot have cyclic dependencies. I could do that in file systems, get cyclic dependencies all the time, and we have to, but that's a separate point of pain. If you can get rid of your cyclic dependencies, then you can make this work. If you have a cyclic dependency, that means that A is derived from B, which was derived from C, which was derived from A. You've got a problem. You're never going to be able to resolve that. In graphs, these are known as what are called directed acyclic graphs, i.e., there is no cycle. This is how we prevent deadlocks in systems. We try to minimize dependencies as much as possible. That fits really well with our goal of optimizing parallelism, because dependencies are inherently not parallelizable. Question. And can I give you an example of a cyclic dependency? Well, I gave one. A was derived from B, which was derived from C, derived from A. So you want something more concrete than that. Let's see, I'm trying to think. All of my good examples from those to Spark. It's easy for an application program to end up with cycles unexpectedly. Usually it's because you plug different modules together, and then you find out that the output of one of the modules is the input of another module. So what you end up with is these loops that you can never actually finish and never resolve, because this one needs to call this function, and this function is here, but then that goes to here. So it is literally a process flow problem. No, it doesn't. But the system, the point here is that Spark doesn't get rid of these. It's the application that has to get rid of these. The application could, in fact, build pipelines that feed one end of the pipeline back into the same pipeline, and that's going to blow up. And we're not responsible for that. This is kind of like what I talked about before, which is one of the things you do in your design is you say, these are the problems I'm going to handle, and these are the problems I'm not going to handle. And in this case, a problem I'm not going to handle is if you're stupid enough to chain A, B, and C together so that C feeds back into A, because all bets are off. We focus on scheduling tasks relative to where their RDDs are located. So this is optimizing the placement of the task relative to the data that it needs to use. And RDDs are a really clean way of encapsulating this, which is one of the reasons why it makes doing this kind of location relative assignment easy. The goals in Spark were to keep data in memory as much as possible to try and minimize the amount of I/O. The benefit of that is you have less data that persists in the execution path, so you don't have the I/O overhead. Often you never need to read the data more than once. And you get more control on the locality. It's local. It's all in memory. There's no storage you have to worry about. It's not going to get propagated to somebody else's memory and then you have to pull it back. But the problem there is that when things go wrong, you may have to do more work. So that's why I said this is a model that only works when failure is rare or the cost of recomputing the work is low. Ideally, both. If the cost of recomputing is high and failure is common, don't do this. It's not a good trade-off. You probably will want to use more of the traditional MapReduce kind of model. RDDs are best used when you have coarse granularity updates with high write throughput. That's why they're right here on that chart. And that's naturally the case for batch workloads. They're coarse, they're big, you're doing a lot of it. And there's an awful lot of batch processing that happens. And RDDs and Spark work really well for that. If you have fine-grained granularity with network-style bandwidth, then that's where you see things like KV storage. We've talked a lot about KV storage. That helps you sort of see that this is a different mechanism. We've been talking a lot about KV storage because they're the database that we tend to replicate, and that's a lot of what we were concerned about. But keep in mind, there are other models in space, and these RDDs are much more batch-oriented. I don't care about the evaluation, and that's it. It was faster. That was basically what the evaluation said. So, anybody have any questions? There's not going to be any questions on the final about this. So this is, again, just a topic of interest, trying to show you that there's a much broader range of things in distributed systems than even what we've managed to talk about. $70,000 nodes. It was big. Yeah. In Silicon Valley, in an undisclosed location. I think it was one of the Supermicro, which is a company that makes rack mount servers, does large scale clusters like that. That's pretty. Probably won't get a chance to, unless you're working at one of the big cloud companies. You'll probably never actually even anything on that size or scale. But then if you go into an actual data center, we'll see that size and scale. And the trick there is that the data centers now are no bigger than they were 10 years ago, but they pack a lot more resources in the same space. What consumes most of the power in a data center? Anybody know? Sorry? Yeah. Heat pumps. Got to move that heat away from the hard drives, the SSDs, the CPUs, the GPUs, the network switches, and you move it out of the building. That's why when you get a sag in the power in Australia and you don't have enough people to restart the chillers, the storage cooks. That was one of the failures earlier. It's air conditioning. It's pretty amazing when you think about it. It's like, wow, most power goes just half the power goes in, well, less than half the power goes into generating the heat, and then the other, more than half the power goes to pumping it out of the building. Because heat transfer isn't 100% reliable. Heat generation is. Cool. Well, that's it for tonight. And we're done. So Thursday is your capstone design. Good luck on that. I will be here on Thursday at 5 to have yet another delightful conversation about another delightful topic.